Welcome back to the last video for today in TEC 259. I think the subject of this video is pretty fun, because it's about perpetual motion machines. And it's just kind of a fun way of thinking about the first law of thermodynamics to look at certain machines and think about why they don't work. Because we know that perpetual motion machines don't work. That is almost kind of intuitive. But the reason why they don't work, it depends on which law of thermodynamics they violate. We're going to have a couple different kinds of perpetual motion machines. And the first kind that we're going to look at today, I've just got, I don't know, maybe 7 or 8 or 9 different pictures of different perpetual motion machines that don't work. And so it's kind of interesting to take a look at them and try to figure out why or how they're supposed to work, and then understand why they don't work. I think that's pretty fun and interesting. So I'm going to go ahead and share my slides. All right, conservation of energy and perpetual motion machines of the first kind. A quick review of conservation of energy, aka the first law of thermodynamics. It tells us that delta U, the change in internal energy of a system, equals Q, the heat added or subtracted from a system, plus W, the work done by or on the system. And remember that we said that if we have heat or work that is added or going into the system or performed on the system, that's positive in our equation. And if we have heat or work that is coming out of the system, for example, the system does work on something else, then that is a negative value that's going to go into our equation. If we have a system that is continuous or cyclical, kind of like a steam system where you can think about a molecule of H2O going around the loop of the steam cycle, or this applies to any of the thermodynamic processes that we talked about in the last video. For example, a geothermal unit, an air conditioning unit, any type of refrigeration cycle, any type of heat pump, any of those are continuous loop type of processes. And if we do have a continuous loop type process and it's operating in steady state, then we have delta U equals 0. And so that is going to tell us that the net heat energy input, Q, equals the net work output, negative W, just by rearranging delta U equals Q plus W, and then setting that equal to 0, we find that Q equals negative W. If that wasn't true, then it would continue to heat up and get hotter and hotter and hotter, or cooler and cooler and cooler, or it would continue to do work on the environment and get larger and larger and expand, or it would shrink and shrink and shrink and get and contract indefinitely. And none of those are true, so that we know that if it's operating in steady state operation, we know that this has to be true, that delta U equals 0, and therefore Q equals negative W. There have been a lot of perpetual motion machines that have been proposed. If they violate this principle, the conservation of energy principle, then we call them perpetual motion machines of the first kind. They're not patentable. So if you send a proposal like this into the US Patent Office, then they're supposed to reject it. And they're supposed to say that this is not something that can feasibly exist. So they will reject that. A good way of thinking about perpetual motion machines of the first kind is if they can continue to do work forever, indefinitely, without a continued supply of energy input, then they are a perpetual motion machine of the first kind. And the reason for that is because we know that delta U equals 0 equals Q plus W, right? So if W is non-zero, and there's nothing else, there's no Q or there's no work input to balance it out, then it doesn't obey conservation of energy. It doesn't obey the first law of thermodynamics. All right, so that's a pretty good way of thinking about it, this last bullet point here. So I have some examples here. Here's one. All right, so does your laptop keep running out of power? No problem. Here's this cable. On one end is a USB connection, so plug that into your USB port on your computer and plug the other into the power connection of your computer, and you'll just charge up your computer by using the USB of your computer, right? So you're trying to get something for nothing. It's going to charge the battery without even drawing anything from the battery to run the USB port, right? So this is clearly a violation of conservation of energy. But it's kind of funny, as a lot of these are. They're kind of amusing to think about. Here's another interesting example. On the left, we have a motor, and that motor is directly connected to a generator. So the generator is being driven by the motor, and the input to the motor is only 12 volts, low voltage, and the output of the generator is 1 to 8,000 volts. So you're getting a much higher output voltage from the generator than you have to put in to the motor, right? So that's a good thing. You're getting more out than you have to put in. That's good. Except it doesn't really work that way. The problem is, well, there's several problems, but one source of confusion here is that voltage is not the same thing as power or energy. So just because you're getting a higher voltage output doesn't mean you're getting more power or more energy output from the generator. So it is possible that you could put a low voltage into this motor, and if you've got it wired correctly, we'll talk about motors and generators later on in the semester. If you got it wired in a certain way, then you could produce a higher output voltage right here, but you still wouldn't want to do that, because even though you're at a higher output voltage, your power output is going to be a lot less. Voltage is not the same thing as power or energy. So you've also got losses inside the system, inside the motor, inside the generator, inside the coupling. There's losses in here as well. So on the whole, you're never going to get more energy output here. You may get a higher voltage, but you're never going to get more power or more energy output than you put into this weird Frankenstein system. All right, here is another one. This one's kind of crazy. We got to think about what's going on with this one. So we have like some kind of a sail car. So we've got this wind turbine in the middle. It's like a wind turbine generator. And this wind turbine generator is capturing the wind and converting it into electricity, which then powers this fan. And that fan blows air to power the wind turbine and to push on this sail to push the whole car forward. All right, so that's a pretty elaborate design. And of course it doesn't work. Of course it doesn't work for a couple of reasons. But even if we could say that, let's say this wind turbine is perfectly efficient, which we know is not true because there's something called the Betz limit that we talk about in TEC 258 and in other classes. But we know that wind turbines cannot be 100% efficient. Nothing can. But even if we did say that this wind turbine was 100% efficient at converting the wind energy into electrical energy, and then even if we said that that electrical energy was powering the fan, and the fan is 100% efficient, which can't be true, but let's say it is. If the fan is 100% efficient at converting that electrical energy into wind energy, then we'd still have a bunch of things that are going to prohibit this from working. We would have to have all of that wind energy from the fan go back to the wind turbine, right? And all of that wind energy from the fan would have to be converted by the wind turbine back into electrical energy, right? So the only way this has any chance at all is if both the fan and the wind turbine are 100% efficient, which we know they cannot be. But even if they are, even if the fan and the wind turbine are both 100% efficient, then in that case, all of the energy from the fan has to go into wind that will go to the wind turbine, right? And the wind turbine has to use that energy. So there isn't anything left over to push on the sail and power this car. So even if we could make the assumption that the fan and the wind turbine are 100% efficient, it still doesn't work, because you can't have, there's no energy left over from what's taken out of the wind by the wind turbine. All of that has to be consumed by the wind turbine, transformed into electrical energy to go back to the fan so that it can produce more wind energy to power the turbine. So you'd have this like loop going around right here. And even if you had no losses, this loop could work. But in this loop, there's nothing left over to push on the sail. So this can't work. Besides the fact that obviously wind turbines are not 100% efficient, and neither are fans. So there's several reasons why this can't work. But this actually does remind me of a different but similar type of idea, and that is to say, why shouldn't I install a small wind turbine on my car as I'm driving down the interstate, right? And then I could use that wind turbine to produce electricity, and then it could charge the battery, or maybe it could drive an electric motor, which would assist my car. And that doesn't work. It doesn't work because the amount of energy that you have to expend, the amount of additional energy that your car has to expend to drive down the road with that wind turbine on it is more than the amount of energy that that wind turbine is going to produce. And that is a consequence of conservation of energy. You're never going to get more output from that wind turbine on your car than the extra that your car has to provide, the energy your car has to provide to drive down the road. All right, so it's kind of a convoluted type of thing, but it won't work. Here's one that's called an overbalanced wheel. And the idea is that this wheel is free to rotate. And each of these arms with a weight on the end is on a pivot, or like a hinge, where it can pivot. You know, I guess this one right here, it can pivot to the left, but it can only pivot down to a certain point, to where it is in this position right here. So this arm can't pivot down anymore. So the idea is that as the wheel is spinning this way, the arms on this side of the wheel kind of tilt downward. And then as these arms cross the uppermost part of the wheel, as they're falling down, they pivot down. And then it exerts more torque on this wheel, which causes the whole wheel to rotate. That's the idea. It doesn't work. The easiest way to see that it doesn't work, and we're not going to do these calculations, but if you were to actually sum the torque on this wheel, the torque is a twisting force, right? So if there is a net torque on this, then it will rotate. But it turns out there is no net torque on this wheel. If you were to actually take the sum of the torques that these weights create on this wheel, it would actually add to zero. Even though this weight is way out here, far away from the center of rotation, and same with this weight here, it's far away from the center of rotation. If you divide this wheel in two right down the middle and count how many weights are on the left side, how many weights are on the right side, so divide it in two up and down right here. So this one's in the middle, so don't count this one. On the left side, we have 1, 2, 3, 4, 5, 6, 7 weights. On the right side, we have 1, 2, 3, 4 weights. So these weights, even though they're farther out, there's fewer weights on the right side of this wheel. And as it turns out, the torques exactly balance so that there is no net torque in the clockwise or the counterclockwise direction. The torque is balanced and it's not going to rotate at all. This one is very similar. It's another example of an overbalanced wheel. The idea is that these weights inside the compartments in this wheel are free to roll inside these compartments. And so as this thing rotates, the balls are going to fall to the outside of the wheel and create a net torque to cause this thing to rotate and to continuously cause this thing to rotate. But once again, if you sum up the torques on this wheel, they would actually balance and there would not be any net torque in either direction. And so it's not going to rotate. This device is called a capillary bowl, and it relies on a phenomenon called capillary action, which I'm sure you've seen before. If you've ever taken a piece of paper and dipped it partway into a glass of water, you've probably observed that the water will actually climb up between the fibers of the paper and it'll actually get the paper wet even above the level of the water in the glass. It'll actually climb up the piece of paper. And this is because of something called capillary action. Capillary action occurs due to intermolecular bonding or attractions between the liquid and the sides of the tube or the glass or the fibers in the paper in that case. And so that actually does cause the level of the water in this narrow tube to climb above the level of the water in this large bowl. So you will actually get a level in this tube that is above this level of the water in the bowl, or whatever liquid it is. But the problem is that those same forces that cause capillary action in the first place, those bonding forces or attractions between the liquid and the sides of this tube, are the very same forces that will not allow it to drip down right here. So you can't have something like this where you have a liquid that is pulled up by capillary action and then it drips down back into the same bowl. It won't work because the bonding, the attractions between the molecules in the liquid and the sides of this tube are great enough that they're not going to allow those droplets of liquid to fall back down into the tube, into the bowl here. If it did work, well, it would violate the law of conservation of energy, because you could put something like a paddle wheel right here, and the water that's dropping down could turn that paddle wheel, which could do work for us. It could drive a generator or move something else. It would do work. And there isn't a continued source of energy input. So it's a violation of the first law of thermodynamics. This next one is kind of cool. This is called the float chain. And the idea behind this is that you've got these kind of like plastic balls that are filled with air, like the balls in like a ball pit at Chuck E. Cheese's or something like that. So you got these plastic balls that are filled with air, and they're all connected together in kind of like a chain. And they're coming down on this chain down below the surface of water, of some body of water. I guess it's the ocean. And then there's a seal right down here. There's like a flap right down here that when the balls get down to this flap, they can pass through the flap, but then the flap seals up again, and it doesn't allow water to get up in this vicinity, in this area. So the balls come down here, and the advantage of having this being air is that you don't have to overcome the buoyant forces of the ball as you're pulling it down underwater, right? And then you do have water in this area over here. So the chain of balls comes over here, and then you do have buoyant forces. And those buoyant forces on the ball over here push the balls up towards the surface of the water. And so you got this chain that continues to go around and around, because supposedly there are no buoyant forces acting on these balls over here, and there are buoyant forces acting on these balls over here. So it's unbalanced in forces, and so you get a rotation. That's the idea. Of course, it doesn't work because it causes this to rotate. It would cause this to rotate, which would do work indefinitely without a continuous energy input. More specifically, the reason it doesn't work is because when you have a plastic ball right here, the amount of force, or the amount of energy that is required to pull this ball through this seal and into the water at this depth, is the same amount of force and the same amount of energy that would be expended in pulling that ball all the way down from the top of the surface of the water all the way down to that position. So it turns out you don't gain anything by having this part be on the left be filled with air and just having a seal at the bottom. It doesn't do anything for you, because you have to expend the same amount of energy regardless. So because of that, there is no net buoyant force acting on this side compared to this side, and so you don't get a torque on this sprocket right here, and you don't get infinite work out of this machine. Here's another one. This is called the infinite generator. So the idea of this one is that you've got this rotor right here, and you've got some bar magnets situated on the rotor. Here's one, here's one, here's one, here's one. And this rotor is allowed to rotate. It's allowed to spin around. Whereas the ones on the outside, here and here and here, these are stationary, but they do spin on their own axis. So this one is spinning around like this, and this one's spinning around like this, and so on for this one and this one and this one, while this is allowed to rotate around. And the problem with this is that it would take more energy to cause these to rotate and to overcome repulsion between these magnetic fields than you would ever get out of this rotating disk in the middle right here. So you're never going to be able to extract more kinetic energy from the rotation of this disk than you'll have to put into the system by overcoming the repulsion between these magnets and just causing these things to rotate, to make these things rotate. But it's a pretty fascinating idea. This one is called the infinite water wheel. And the way that it purportedly works is that you have a reservoir of water up here on the top, and then you have a narrow hole through which the water flows and falls down here, and it falls on this water wheel right here. And so the weight of the water in these buckets in the water wheel causes this water wheel to rotate. And then this water wheel has some gears on the outside, which meshes with this gear, which causes this gear to rotate around like this. And then this gear has a connection to a rod right here, which is going up and down. As the gear is rotating, it causes this rod to go up and down, which operates a pump, kind of like an old-fashioned water well pump where you had to pump it and it brought the water up out of the ground. And so it's operating this pump, which is bringing the water from the lower reservoir down here where the water falls after it falls out of the buckets of this water wheel. This pump brings the water from the lower reservoir back up to the upper reservoir where it repeats the cycle over and over and over again. Clearly, it doesn't work. We know it can't work because you're getting a work output. I mean, you're getting this rotation of this water wheel and the rotation of this. So this could be connected to do some work. If you had it connected to a generator or a pulley system or something like that. So it could do work without an externally supplied source of energy. So we know it doesn't work. And there are a couple of problems with this. Number one, you could say, probably the most obvious thing is that, well, nothing in here is perfectly efficient. So definitely there's friction in the bearings here. There's friction in the gear teeth when they mesh here. There's friction in the water pump right here. So you're going to have losses in this system. But that's actually not the only reason why it doesn't work. Another reason why it doesn't work is because when you are dropping water from here down here, notice some of the water is going to have to spill out of these buckets as this thing is rotating around. Some of the water is spilling out. So that when it spills from here to here, that is potential energy that is being lost by the system because this system is not recovering any of the potential energy that is lost as the water falls out between right here and right here. So that's not being converted into kinetic energy of this wheel, and therefore that's not being converted into this wheel, and that's not being converted by the pump into raising that water from the lower reservoir to the upper reservoir. So because you're not taking advantage of the full potential energy between here and here, the only hope you would ever have of being able to restore that water up to its original height is if you can take advantage of the full amount of potential energy on the way down, right? If you could take advantage of that full potential energy of the water going to the lower reservoir, and if there were no inefficiencies, if all the bearings and gear meshes and everything was perfectly efficient, then it might be possible. But the fact of the matter is there's several things preventing it. Number one, you have friction and losses. And number two, you're not even taking advantage of the full amount of potential energy from the upper reservoir to the lower reservoir because some of that is falling out of the buckets as the water wheel is rotating. So you're not converting all of that potential energy into kinetic energy. And thus, you'll never be able to get all of that water from the lower reservoir back to the upper reservoir. All right, but it's a pretty cool design, nevertheless, like a lot of these are. This next one is a real head scratcher. It appears to be a perpetual motion machine of the first kind, but it's actually not. And it's really interesting to think about. It just kind of plays with your mind a little bit. It's called Dead Downwind Faster Than the Wind. And the idea is that the wind can actually push this vehicle downwind with the direction of the wind. It can actually push this vehicle that's specially designed it can go faster than the speed of the wind. All right. There's no motor, there's no batteries or anything on here. It's just powered by the wind, but it can go downwind faster than the speed of the wind, which at first just seems like can't be right. And if you want to dive into a rabbit hole of reading about this stuff, I've done it. So believe me, it's kind of a rabbit hole. Do a Google search on DDW FTTW, stands for dead downwind faster than the wind. There's a lot of information about this on the internet. But it is true, actually. It really does work, and it's not a violation of the first law of thermodynamics. The way that I think is most helpful for me to understand how this is working is to first just ignore the propeller. So just say there is no propeller on this thing. All right, so it's just a car on wheels, but there is no motor or anything. And so the wind is going to push it. You know, there's going to be some drag on this vehicle, and the wind is going to push it. All right, just at a certain speed. All right, now what we're going to do is we're going to take one of the wheels and we're going to take the axle from that wheel and connect a gearing system with some drive shafts and some gears. And that gear is going to drive a shaft that comes up here and spins a propeller. All right, and that propeller is designed so that as it spins around, it also exerts a thrust backwards, which is trying to push the car faster. All right, so that's actually going to push it faster than the speed of the wind, which is just kind of weird to think about, but it really does work. It's a drag device. I mean, it's being dragged by the force of the wind, but then also the propeller is being driven by the axle of the wheels. So it's not, you know, one way that it might be confusing is if you think that the wind is acting on the blades and the blades are driving the drive shaft to drive the wheels. That's not the way it's working. The power is going the other way. So it's actually getting up to speed, and then the drive shaft from the wheel is actually driving the propeller shaft, which causes the propeller to spin, which pushes it faster than the speed of the wind. It's kind of mind-boggling, but it really does work. One other thing that might be helpful to recognize, actually a couple more things. First of all, there's no such thing as conservation of velocity. So there's nothing that necessarily says that you can't have an object that is propelled by the wind that goes faster than the wind. Now that's kind of weird to think about, but here's another proof that it actually works. I don't know if you have any of you have any experience sailing in a sailboat. I've done a little bit especially when I was younger. There are not many places to sail around here, but I did have a small sailboat when I was in high school. And we had a small lake that was not too far away from our house. Anyway, it turns out that if you're sailing in a sailboat and you are going at 90 degrees or approximately 90 degrees to the wind, so the wind is coming in this direction and I'm sailing in this direction, you can actually go faster than the speed of the wind. Now, you're not going downwind faster than the speed of the wind in a sailboat because there's nothing like this arrangement on a sailboat, but you can actually go faster on it's actually called a beam reach. A beam reach is the angle that you're on if the wind is coming approximately on your beam, so off of your side. You can actually go faster this way than the wind is coming this way. So that kind of also helps motivate the idea that this could be possible, that it's possible to go downwind faster than the wind if you have this specially designed vehicle that can take advantage of aerodynamics as well as the drag from the wind pushing on the vehicle. All right, that's going to wrap up our discussion of the first law and the zeroth law of thermodynamics. I hope you enjoyed seeing those examples. I really enjoy seeing those and thinking about why it is they don't work. Some of them, like I said, are kind of head scratchers. You got to sit there and think about it for a little while. I will do a quick review of problem set number 4. So to do that, I'm going to switch over to the document camera. Here's problem set number 4. In number 1, we've got a sealed rigid vessel, and it contains 2 kilograms of fluid. It's being both heated and stirred at the same time. All right, so heat is Q, and it's being stirred. That's an example of work. That's one of the examples we gave early on in the class of a kind of work. The internal energy of the fluid at first, before those things are done to it, is 400 kilojoules per kilogram. Don't forget it has 2 kilograms inside there. And we got some heat transfer. Q is 400 kilojoules per kilogram. And also this propeller does 50 kilojoules per kilogram of work on the fluid. So what's the total internal energy content of the fluid after these processes have been done to it? So this is a direct application of the first law of thermodynamics. Remember, we had delta U equals Q plus W. So the change in internal energy is equal to Q plus W. All right, so think about the sign conventions and solve for the final internal energy of it, given that we know what the initial internal energy of the fluid is. Okay, so that's about it for number one. Number two is really similar. We have a sealed rigid vessel. It has 2 kilograms of fluid. Again, it's stirred by a propeller. And this time, it's not quite as clear what is the work that's being done. So we know it's being stirred, and that is work. But how do we calculate that? Well, the propeller rotates with a torque of 150 Newton meters, and it completes 200 revolutions. So we haven't really talked about how that would be work, but fortunately, I give you an equation down here. The work is equal to the force times the distance times cosine theta. That's what we've used so far for work in this class. But also, for something that's rotating around, like stirring, work is also equal to the torque, that's the twisting force, times 2 pi, that's just a constant, times N, where N is the number of revolutions. So really, this equation is just the rotational equivalent of this equation, which is the linear mechanical. So this is like the rotational mechanical equation for work, and this is the linear mechanical equation for work. Like if I'm just pushing something along, that would be force times distance times cosine theta. This is for when I'm rotating something. All right, so now you have a way of calculating what is the work being done on the fluid inside this vessel. So you know the torque, you know the revolutions, number of revolutions, so you can calculate the work. And also at the same time, 100 kilojoules of heat is lost to the surroundings. And we're given the initial internal energy. So once again, find the final total internal energy of the fluid. Once again, this is a direct application of the first law. Delta U equals Q plus W. Keep track of what's being added and what's being subtracted, and make sure you note that some of these are per kilogram and some of them are not. So make sure you keep track of all that and find the final total internal energy content of the fluid. And then in the last one, we are making an application to a steam system. And we've got our basic components of a steam system, a boiler, a turbine, a condenser, a feed pump. And we are shown how much heat input we're getting to the system in the boiler, how much work is being provided by the turbine, and we know how much work we're putting into the system by the feed pump, and we don't know how much heat is being rejected by the condenser. But this is exactly why we're talking about the first law of thermodynamics. And so by accounting for the different inputs and outputs in this system, we can calculate this. So you can apply the first law and you can calculate how much heat is being rejected by the condenser. Delta U equals Q plus W. Part B is kind of, well, it's a little bit subjective, I guess. It asks, what's the power capacity of this system in megawatts? Well, what does it mean by power capacity? Power capacity of what? So think about that a little bit. We talked a little bit about this in the last video in the sense that what is the useful output of this system? What are we using this system for? So once you think about what is the useful output of this system, then you could think about what is the power capacity of this system. All right, so it's a little bit vague. This is meant to kind of stretch your thinking a little bit. How would we rate this system? If this was a power plant, how much power would we say that this power plant is producing? All right, that's probably the best way of thinking about it. If this was a power plant and it had these parameters, we would call this a power plant that produces how much power? What would we say? What do you think? As always, we will review problem set number 4 at the beginning of the next class. So problem set number 4, as usual, is due at 10 a.m. At the beginning of the next class. So that's going to wrap things up for the topics today about the zeroth and first law of thermodynamics. Let me know if you have any questions about any of that stuff, and I will see you in the next class. Have a good week.